So let's look at the oxidation of alcohols. In 12.4, we made alcohols by reducing, and now we're going to do the reverse process, oxidation. We're going to get rid of our alcohols. Primary alcohols can be oxidized twice because they have two hydrogens. And so you remove one, you get the aldehyde. You remove both of them, you get a carboxylic acid. Secondary alcohols can only be reduced once because they've got, oxidized once because they've only got the one hydrogen, and they make a ketone. Tertiary alcohols cannot be reduced because they don't have any protons at the alpha position. There are a large number of reagents available for oxidizing primary and secondary alcohols, and many of them are formed from chromium trioxide or from sodium dichromate. And what these compounds make is chromic acid. Chromic acid is very toxic for the environment, and I'm told that this reaction is not used in industry very much anymore because of that. The mechanism here is going to be that the alcohol and the chromic acid are going to make this ether. This reaction is fast and reversible, but once it's made, the proton here can be snatched away and you end up with this nice ketone. Doesn't write very well with a highlighter. Okay, so the oxidation of a primary alcohol with chromic acid, you end up with the carboxylic acid. You do not end up with the aldehyde. So this reaction tends to go all the way to completion. And like I said, the chromic acid has been replaced with greener chemicals. And one of those is the PCC, pyridine chlorochromate. This allows the isolation of the aldehyde if the substrate is primary and ketone if it's secondary. Schwerin oxidation uses dimethyl sulfoxide and oxyl chloride. These form a chlorodimethyl ion and also produces primary alcohol, produces an aldehyde, a secondary alcohol produces a ketone. It does not produce the carboxylic acid. The third one here is the Dres-Martin DMP oxidation. This is an even more environmentally friendly compound, and it also produces aldehydes and ketones from primary and secondary alcohols. So let's predict the major organic product that can be made in this reaction. First, we want to identify whether we've got a primary or a secondary alcohol, and this is our alpha carbon. It only has one R group off of it, so that makes it primary. If it's primary, do we make the aldehyde or the carboxylic acid? Well, this is the chromic acid, and it will take it all the way to carboxylic acid. I'm not going to say too much about biological redox reactions. NADH is the most important reducing agent in biological redox reactions, and it looks like this, a very complicated molecule. The part we're interested in is this reactive center. The NADH functions as a hydride delivery agent, a lot like our sodium borohydride or our lithium aluminum hydride. It can reduce ketones and aldehydes to form alcohols, and this is used in the body. If you drink methanol, which I don't recommend, your NAD plus will take off one of the protons and make NADH. This makes formaldehyde. And if you take off another hydrogen, we end up with formic acid. These are toxic compounds. They cause blindness and death, which is why I do not recommend that you drink methanol. If someone has methanol poisoning, the treatment is interesting because the treatment is to give them ethyl alcohol, or the regular alcohol that people normally drink. And the reason for this is that ethanol binds more strongly to this alcohol dehydrogenase than the methanol does, and ethanol produces acetaldehyde and acetic acid. These will cause nausea and vomiting and the other hangover symptoms, but you can avoid blindness and death. So if you ever go to the ER with methanol poisoning, they will give you a drink.